When atoms come together, they form molecules. And for life, the most advantageous bonds are when atoms are coming together and storing energy. And then when you break those bonds, you're able to release or harvest that energy. Now, there are other chemical reactions where this is not the case, but these are the ones that we encounter the most in living systems and talk about the most, is the ones where binding stores and breaking releases. So there's 3 or 4 major types of bonds that we talk about. The simplest ones is when one of those cations becomes attracted to one of those anions, because they're like little magnets, they're charged, and they stick together. We call this an ionic bond. They form substances called salts. And I know when I say salt, you guys think table salt, like to sprinkle on your dinner. But salts are a really common form of substances in our planet. And so chemically, to say it's a salt is to say that it's an anion combined with a cation. These things have kind of moderate strength. They're non-malleable, which means you can't shape them. You can crush them and they will shatter apart, but you can't mold them like Play-Doh or like metal. They don't change shape, they break. So here's how sodium and chlorine create an ionic bond. The sodium has one of its electrons and passes it over to the chlorine. Now the sodium is a cation and the chlorine is an anion, and so they want to be near each other. The other type of bond that's very common are called covalent bonds. And in a covalent bond, they share electrons. And so the electron is going to travel first around one atom, and then it's going to go travel around the other atom and go back and forth and back and forth. Okay? If they do that nice and evenly, like in this image, we call that a nonpolar covalent bond because both of the sides are equal. So I kind of think of it as they have joint custody of the electron. In other bonds, one atom is larger than the other or electrically stronger than the other. And so it doesn't spend equal time. So like over here in this water molecule, hydrogen is so small that the electron only can stay around it for a very short period of time. And then it takes a big long trip around oxygen, which is a much larger molecule. So its trip is unequal. You know, its path looks more like this. Okay? It's kind of like they have, you know, primary custody and visitation of that electron. And in that case, it actually creates little charges on the molecule. So if you looked at a water molecule actually has a head and a tail. And the end where the electron spends very little time would be somewhat positively charged over here by the hydrogens. And the end where the electrons spend a lot of time over here by the oxygen becomes slightly negatively charged. And that means that water molecules are actually going to be attracted to each other, and other molecules with this type of bond will be attracted to each other. When that happens, we refer to these as hydrogen bonds or hydrogen attractions. They're not really bonds because there's no electrons being shared or exchanged. They're just two molecules that want to be close to each other. So the real chemists in the room will be offended by the name bond, but that's okay. I think of it kind of like a handshake where these molecules will go and they'll mingle with one atom, and then they'll go off and mingle with another molecule, and then with another molecule, and then with another molecule. And we see that particularly in water, where these hydrogen bonds or hydrogen attractions are constantly shifting and changing. So this is an attempt to show hydrogen bonds between water molecules, not in water molecules, but between the water molecules because of those attractions. So little dotted lines are there, and those are going to shift and change. They're not just going to stay stable. Because water has these internal attractions, and because of these shifting attractions that it has, that means that water has some really cool characteristics that help life be possible. one of the most basic ones we've kind of already talked about, that water's sticky, that it's constantly wanting to connect to itself. Water is attracted to water. And so those water molecules not only want to stick to each other, but they also want to stick to other things. So if you think about like when rain falls on the window of your car, well, first of all, it wants to stick to the glass of your window, right? But then two, it wants to join together and form larger and larger droplets because it wants to stick to each other. This creates characteristics like surface tension, bubbles, and capillary action. And those might not seem like a terribly big deal to you, but surface tension creates an edge between wet and dry in the universe. And in a lot of environments, there's more life living at the surface, at that edge, than there is in almost any other part of the environment. Bubbles are important because at the end of the day, that's what our cell is. It's a bubble surrounded by a layer of fat that controls what can move in and out of the bubble. And then capillary action is a big deal because this is how we move fluid through tubes. And moving through fluid through tubes, like blood through your vessels or like sap through a plant, both become really critical because organisms that moved to land and live primarily on land and are large need to have a way to transport fluid through their body. Another characteristic is that water is typically liquid at room temperature. Might not seem like a terribly big deal, but if you look at other molecules of similar size like CO2 or carbon monoxide or sulfur dioxide or nitrous oxide, those are all very similar in size, and yet they're all gases. And if water was a gas at our Earth temperatures, then we would have no fluids to work with. Water changes temperature very slowly. This is sometimes referred to as water having a high specific heat. And this means that water doesn't boil quickly, and it also doesn't freeze quickly, which is critical because it gives us time to react to temperature changes. If life didn't have time to respond to temperature changes, it probably wouldn't exist. Next one is called a high heat of vaporization, or that it takes energy with it as it evaporates. And this is really useful to us because it helps moderate temperature and regulate temperature. And so as we get hot, water will evaporate away and take that heat with us. When we're cold, we can move water to areas as an insulator, actually. Frozen water floats. Because frozen water ice floats, it actually creates what we call convection, which means that temperatures on Earth are kind of the average of the cold and the hot that is going on in the world around us. So if you think of this as, this is a side view of the ocean. The coldest water in the ocean is down at the bottom, which means that ice typically forms down here at the bottom. But because it floats, it rises up to the surface where it warms and melts and sinks back down to the bottom. So this is creating a circulation and makes all the temperatures less extreme than they would be otherwise. If ice instead froze at the bottom and stayed sunken at the bottom, then the ice would just grow and grow and grow, and our planet would be covered over in ice. Water is a solvent. Now this is a huge one because it means it can separate atoms and molecules. And a lot of times, the individual atoms and molecules are more critical than the whole. So sodium's a great example because sodium chloride, table salt, is something that we consume often more of than we should have. But sodium chloride isn't useful to us in that form. In that form, it's a crystal. It's got sharp edges. It would damage things. But if we can split the sodium and take it off to do one job and the chlorine off to do a different job, it can be useful to us. And so water can make that separation and keep them separate. When our bodies aren't doing that properly, we see things like kidney stones and gallstones, where salts are crystallizing in our body rather than being dissolved and um, soluble. In addition to that, water is itself able to be broken apart. And when you break it apart, this might not look like it's breaking evenly, but it actually is. Let me take you over to my other sheet here really quick. So water, when it breaks, first will split where the OH separates from the other H. And this guy here we call hydroxide. Very, very useful part of producing a lot of the alkalis or bases that are in our bodies. This hydrogen over here, however, doesn't like to be by itself. I think of hydrogen ions as the clingy girlfriend of chemistry. And so as soon as it finds something to attach to, it'll attach to that. Well, since water is the most common thing in our world, what it's most likely to attach to is more water. And that'll give us hydronium, H3O+. And so the chemists will forgive me for talking about hydrogen bonds as if they were bonds, because I'll tell you that these hydrogens never hang out by themselves. They join with water to make hydronium. And this is the foundation for most of the acids that exist on our planet. So acids are anything that produces a high level of hydronium when it is mixed with water. And bases are typically defined as things that produce high levels of hydroxide when they're mixed. When we talk about acids and bases, we typically bring up the concept of pH. pH is a measurement that runs from 0 to 14, and it's in a negative log scale, which means that small numbers mean there's a lot of hydronium, and big numbers means there's very little. You might, Mary, what are you talking about? This is crazy. But here's the deal with the negative log scale. Okay, if you have a pH of 1, that's a concentration of 0.1. If you have a pH of 2, negative log means that that is a 0.01 concentration. If you have a pH of 4, that would mean 0.0001. It's the number of decimal spaces is that number. If you have a pH of 7, that would be 0.1, 2, 3, 4, 5, 6, 7. If you have a pH of 10, okay? And so that's what it means that this is in a negative log scale. It means your small numbers are a high concentration and large numbers give you a low concentration. So acids tend to have low pHs, high concentrations of hydronium. Things like stomach acid, beer, coffee, urine, saliva even falls in this category, although some people would say that it's more neutral. I'm going to save neutral for very specific things because saliva, if it's 6.7, is technically an acid. Our neutrals are neutral because they have a balance of hydroxide and hydronium. So they should have a pH of exactly 7. Things like pure water, take tears off of there. Most tears are not actually perfectly neutral. But salts are perfectly neutral because when they split, they are typically not acidic or basic. And then the alkalines or bases are much rarer in living things. They're around us in our environment, but they're not typically things that mix well with living things. So these ones have a low concentration of hydronium, a high concentration of hydroxide. And so they have pHs of greater than 7. Blood is actually an alkali. Antacids like your Tums or your Rolaids are going to be antacids. Ammonia, which is a common cleaner. And then oven cleaner, which you may actually know as lye in the old-fashioned ones. The newer oven cleaners are made differently, but if you get one of those good old-fashioned ones that are like open up all the windows in your house and put on gloves and a mask, Those are the good old-fashioned lye-based oven cleaners that are super corrosive. A lot of people think about acids being corrosive, but don't realize that bases or alkalis can also be very corrosive. So when you're in that neutral zone, that 6, 7, 8 pH, things are pretty straightforward. But as you get down out on the edges, the 1s and 2s and the 13s and 14s, that's where pH is really kind of extreme, and an extreme acid can be just as dangerous as an extreme base. Understanding how acids and bases work and chemistry is a big part of how we regulate the chemistry of our bodies. One system that you can use to control pH is called neutralization, where you mix an acid and a base, and what you get is water and salt. And this is very predictable, that if you mix an acid and a base, you'll get water and salt. In general, that seems like a fine way to control and regulate things, but the sidebar to that is that when you mix a strong acid with a strong base, it can be a really violent reaction because they're so far away from neutral that it can be difficult for them to make all of those chemical exchanges and not create some form of an explosion. I actually had a gal in the lab one time who hadn't really thought about it and was mixing together a fairly strong acid and a fairly strong base and had a beaker explode in her hand. So while it's useful and functional, if you get too far away from neutrality, it can also be dangerous. Buffering, on the other hand, uses substances that are not acids or bases. They have a pH of roughly 6 to 8 and can absorb either hydroxides or hydroniums. So they're really playing both sides of the fence, which is cool, because that's a very rare occurrence to be able to shift both the atoms involved in acids and the atoms involved in base and absorb either one of them. That's all for the basic chemistry. I'll move on to the biological macromolecules of carbohydrates and lipids in the next video, and then there's a second video that does proteins and nucleic acids.